Alright folks, so in this video what I wanted to talk about is how you can build better RAGs with ColBERT. So ColBERT stands for Contextualized Late Interaction over BERT, right? So previously ColBERT was introduced by this paper which came from Stanford, and they kind of use this for better information retrieval, right? So what we will do in this video is we will use ColBERT to get better results in terms of RAG. And first we will go through what are the typical issues of general RAG architecture, and then we will talk about how the ColBERT can help us to resolve those issues, and in the end we will talk about the code implementation of ColBERT, where we will leverage ColBERT to build a RAG pipeline, right? So with this, let's get started. First, we will talk about what are the issues with RAG typical architecture. So in the typical RAG system, what we have is we get a domain-specific or proprietary document on top of which we want to build the RAG system. So once we have that document, then what we do is we create chunk out of those documents based on the chunk size. So you can see here we have chunk 1, chunk 2 till chunk n, right? So then we pass these chunks through a embedding model, and we kind of compress the whole information of that chunk into a single embedding vector, right? And we kind of expect that the whole information that is present in each of these chunks will be incorporated in these embedding vectors, right? And typically the size of these embedding vectors are like 1536, which is typically the size for OpenAI embeddings. And after that, once we get the embeddings, then the query comes from the user. The query goes through the embedding model, and we also create a query embedding. Once that is done, then we kind of compare the query embedding to each of these chunk embeddings, and based on the similarity score, which is typically a cosine similarity score, we fetch the top k chunks, right? So that is typically the architecture of a general RAG pipeline, and we kind of expect a lot from this embeddings vectors, and we kind of expect that the whole chunk information which can be incorporated in this single embedding vector for each of the chunks, right? So which may not be the case always, right? So whatever the embeddings vectors we are getting, that may not capture all the important informations that is present in the chunk, and due to this compression of this whole chunk into the embedding vector, we may lose some crucial information, right? So which we typically try to solve using ColBERT. So that I will go through. So you can see these are the embedding models which is currently at the top of the leaderboard, which is hosted in Hugging Face. You can see like these are the embedding dimensions which we have, like the rank 1 embedding, which is NV embed v2, has an embedding shape of 4096, right? So whenever we will create a chunk using this embedding model, so that the shape of that embedding vector will be like 4096, right, for this embedding model. So this is what where we are trying to explain that all the information that is present in a single chunk may not be represented with a single embedding vector, right? So that's what we will try to solve using the ColBERT. Now let's see what this ColBERT is and what are the typical steps that we need to follow to create late interactions using ColBERT. See, we have this query which is given from the user, and we also have the corresponding each of this document. So this is you can think that this is a single document what we have. Then it goes through a BERT model, and we only consider the last layer's output, right? And you can see this query is divided into each of this token, right? So this is one token, this is another token, and this is the last token of that query, right? So for each of this token we extract the last layers output value using BERT. So this is what we will consider as the first token representation, this is the second token, and this is the third token representation using BERT, right? So similarly we create a token level embeddings for the document. So this document's last output layer output is this one, where we have the token level embeddings for each of these uh, tokens for the same document, right? So once we get that, what we will do is we will do the step 2. So in the step 2, what we do is we create a matrix, and in the matrix we kind of use a dot product to kind of get the similarity between the query tokens to the each of the document tokens. So this is the row which tells you like what is the similarity score of the document tokens with the query token 1, right? So similarly, this is the similarity of the document tokens with the query token 2, and this is the score which is related to the document token similarity with the third query token, right? So we can get this score for each of the document tokens, and then what we do is we kind of fetch the maximum similarity score for each tokens. So you can see for this query token the maximum similarity score is this one, and similarly we have the other max scores, right? So this is what we are calculating here is the interactions between each of the query tokens with each of the document tokens, right? And then we kind of select the maximum similarity, and what we do after that is we calculate this maxim, which is the sum of these values, right? 0.85, 0.84 and 0.97, right? So this is actually the similarity score for this query with this document, right? So similarly we do it for this query with the other documents that are present in the vector db, and then we can kind of select the top k documents using this mechanism, right? So in our case you can imagine that these documents are nothing but chunks, and the chunks will be also splitted into individual tokens. So whatever the chunk has, so for each tokens we will get the corresponding token embeddings for that chunk. So and then we will calculate the maxim for each of these chunks, and then we will select the top k chunks using this mechanism, right? So as we are doing this similarity calculations at the very granular stage, like at the token level, we are calculating the maximum similarity and the maxim score for each documents or chunks, and then we will calculate like what are the top k document or chunks, right? So this is another example where we kind of leverage the maxim. You can treat it as a query token embedding, and this is the document embedding, right? And then we kind of calculate for each of the query tokens what is the maximum score with the other document tokens, right? So transformer will have a max similarity score with this token in the chunk, and come will have a maximum similarity score with released, and then when will have a maximum similarity score with August and 1986, which is the year uh, for this token, which is related to when. So in that way this comparisons will be done, and then we will calculate the maxim for this particular document, right? So this is what we are doing here is we are doing a late interactions between the query tokens and the document tokens. So the document tokens embeddings will be created at first, and then that will be stored in the index, and when the query comes, then the query token embeddings will be calculated, and then we will calculate the maxim with each of the documents, right? So this is that is where the late interactions between the query token and the document token happens, and based on that the top k chunks or the top k documents will be selected, right? So with this concept, now let's go through the code and see how we can implement a rack pipeline using ColBERT. See, we will first do the installation. So one of the library which you may not be aware is this Ragatoli. So using that we will leverage the ColBERT, and we will do the contextualized embedding creation for each of the documents, right? So then what we will do is we will initialize this model of ColBERT. So you can see we are leveraging ColBERT 2, and we are creating a object which in the name of that object is rag. So then what we will have is we will have the source document. So I am using a blog post as a source document, and from that blog post where we will scrap the document and we will create a variable which is like blog docs, right? So then what we will do is we will get the page content of that blog post, and we will create a variable which is doc, right? So using this doc, what we will do is we will create the chunks using ColBERT, and then we will push it to a index, right? So you can see here the index creation process is going on, where we will, using this rag object, we will do this rag.index, and there we will pass the document. Then we will give a name to this index, which is agents. Then we have this parameter called max document length, which is nothing but the chunk size, what we typically use whenever we are using a recursive character text splitter or any other text splitter to create the chunks, right? So then we are mentioning that split documents equals to true, which means that based on the size of this max document length, the multiple docs will be created, and based on that, the token level embeddings will be created for each of these documents, right? So it takes a bit of time to create this index, and then what we will do is we will create a LangChain retriever. So using this rag, what we will use is as LangChain retriever, and then we will convert this ColBERT index to a retriever. So then what we will do is we will call this retriever.invoke, and we pass a question, tell me about agents. Then it will fetch uh, the relevant documents or the chunks using the late contextualized late interactions what we have discussed so far, right? So once that is done, then we will create a rack pipeline. We will initialize a LLM, and then we will create a chat prompt template, and we will create a prompt out of it. Then we will create a retriever chain where the context will be fetched using the ColBERT, which is typically the retriever here. And then what we will do is we will create this retriever chain, and once that is created, we can invoke with a certain question. So we can write retrieval chain dot invoke, then we can pass a question which tells you what is task decomposition in agents, and we will get the corresponding output. Okay, so this is all I wanted to discuss in this video of ColBERT, where we leverage the concept of contextualized late interactions using BERT. So this can be an interesting way to solve the issues with present architecture of your RAG, but I believe like this is a bit time consuming. It has a lot of complex calculations at the token level. So maybe instead of using for a real life application or a real time application, you can go for the RAG applications which can run in the backend or in offline manner, and then it can generate the output based on the user prompt or a developer request, right? So this is all I wanted to cover in this video. Thank you for your time. See you in the next video.